Alright, so today we are going to start two new topics, binary search and heaps. And before that, I would like to make one reminder about recursion. Like one of the problems that you solved, it actually showed you a very important case when it comes to dealing with recursive codes. It is very probable to implement a code in which you can you can basically solve the same sub-problem again and again. And the perfect example for such situation actually happens once we deal with the problem of Fibonacci numbers. So, is everyone familiar with the problem? So just to make sure everybody has the concept. In the problem, we are supposed to calculate the nth Fibonacci number. And Fibonacci numbers are very similar to Fibonacci numbers in the sense that the formula is like that. So Fibonacci n is equal to Fibonacci n minus 1 plus Fibonacci n minus 2 plus Fibonacci n minus 3. And it starts with 1, 1, 2. So this number is 4, this number is 7, and this number is 13, and so on. So I guess everybody is clear with the definition, right? So the first trivial solution that comes to mind by using recursion is something like that. So we get our n value. If n is less than 2, let's say this is Fibonacci 0, this is Fibonacci 1, and so on. So if n is less than 2, then we just return 1. If n is equal to 2, then we return 2. And otherwise, we just return Fibonacci n minus 1 plus Fibonacci n minus 2 plus Fibonacci n minus 3. So, do you guys think that this code is going to calculate the correct Fibonacci number in cases where the result fits into integer? I mean, theoretically it should do that, right? But do you also think that is it making any unnecessary calculations? Right? So, in order to understand why this is making some unnecessary calculations, let's take a look at the tree for the call of Fibonacci 6. So 6 is greater than 2, therefore we are going to hit to this line. And Fibonacci 6 is going to call Fibonacci 5, Fibonacci 4, and Fibonacci 3. So Fibonacci 5 here is going to call Fibonacci 4, Fibonacci 3, Fibonacci 2, and 4 is going to call Fibonacci 3, Fibonacci 2, Fibonacci 1, and 3 is going to call Fibonacci 2, Fibonacci 1, and Fibonacci 0. So let's see. Okay, let's also open this one finally. I'm not going to make it complete because we have too many sub branches and limited time. Fibonacci 1. So, like, obviously we have some other calls, or maybe not for these guys, but like this one, and for this one. But like one thing you see here is we have the same element appearing multiple times in our tree. So if we look at how many times we are actually calculating Fibonacci tree, like the first calculation is here, the second one is here, the third one is here, the fourth one is here. So we basically solve the same sub-problem again and again. Like, is the number that we are gonna get at the end of the calculation gonna change? No. Like, if we calculate Fibonacci tree, we will always get the same result. However, since we do not do anything about this usage of the same sub-problem solution again and again, it's going to be recalculated again and again. And this is very inefficient, and this is something that we want to avoid. And there is a very simple way that we can avoid this in our such recursive implementations. And the technique is called memorization. And the idea is, basically, once we calculate the result, we just save it to an array or list or vector or whatever, and then whenever we are looking to calculate a new value, we first check whether the result was already calculated, whether that sub-problem was already solved before. And if that was the case, then we directly return the result. And if not, we calculate it, because it's the first time we face with the sub-problem. So if we apply this idea here, what we are going to do is, instead of returning the result as we calculate, we are going to save it. Let's say we are going to put it in our result array. And we are going to say the nth element of this array is going to be equal to this calculated value. And in the end, we are going to return our results. I mean, you can also do it in one line. It's just I don't want to have super long line right now. That's why I write it like this. So, if we do this, do you think that it's going to be enough? No. Now we are saving it, but we are not checking whether the value that we are about to calculate, the sub-problem that we are about to solve, is solved before or not. That's why we need to insert here a check for that, which is if res n is greater than 0. Because in this problem, all the numbers we are dealing, they are positive, right? So that's why if we initialize our res array with 0 and we just check the positivity in this array, that would be enough to tell whether that sub-problem had already been solved in the previous calls or not, right? So if this is the case, then we are just going to return the result that was already calculated, that had already been calculated before, like this. How about now? So now, do you guys think that our code is still solving the same sub-problems again and again? No, right? Because now we are checking whether we had solved this sub-problem before or not, and if that is the case, then we directly get the result from the result array, rather than iterating through the code and calculating the result. And if we are facing with the sub-problem for the first time, in that case, the res n is going to be 0, like assuming we initialize this array with 0 value at the beginning, then we will basically go ahead and calculate the result for the sub-problem. So this way, instead of making all these subcalls, let's say Fibonacci 4 was calculated here for the first time, then we are not going to have any of these subcalls anymore. Like basically, this call directly is going to return res 4, because it was already calculated here. So is everyone clear with the idea of memorization? And you can see how useful it can be, right? Because without that, since you're solving the same sub-problem again and again, it's very likely that you're going to get time limit exceeded. And you're going to be doing a lot of inefficient calculations, basically. Unnecessary calculations. But with the help of memorization, we can do that. Okay, so any questions about memorization up to this point so far? No questions? Things are clear? Perfect. All right, in that case, let's continue with our new topics. So, the first one is binary search, and we had already covered binary search trees. If you remember, I gave you one homework after that lecture. So, like with hash maps, for example, we can easily, or like with hash sets, we can easily keep track of what values appeared in a given stream and say, okay, so whether this value exists or not. Because that was the purpose that we used binary search tree right after implementing it, if you remember. Like basically we were checking whether this value exists or not, and we were checking the value that we are looking for like against the value in the root, and if our value is greater than root's value, then we were going to the right subtree. And if our value was smaller or equal to the root's, or smaller to the root's value, we were going to the left subtree. And if it was equal, then we were returning true. So, and we, like, assuming our binary search tree is not very well balanced, the worst case can go up to n for such search, right? Like, assuming like we have everything in sorted manner, and then we insert them all in our binary search tree, so we have something like a linked list. And if we are looking for the latest element, then we have to go through, we have to iterate through the whole list. And this was inefficient. And at the same time, we said for the same problem, we can actually use like hash sets. We can put things into the set and then check whether a given element was already included in the set or not. And we can do this operation, like the queries, in constant time. So, then what is the advantage of using binary search tree? Like, is there a place that we cannot directly apply our hash set algorithm, and actually we may be in need of using binary search? So did anyone make a research about that? Did anyone do the homework? Nobody? Okay, so please next time, let's have at least one guy who does the homework. So, let's think about it. Let's say our problem is not about finding whether a given element exists in our array or not. Let's say instead of this, our task is to find the closest element to a given element. So in that case, would hash set be useful for us? Like, what can we query with hash sets? Right? But if it's like just greater, a little greater or a little smaller, then unfortunately hash sets are not very helpful. So that's why, like, there are some applications where we are not looking for exact match, but we are looking for a value that is like very close, or like the closest value for a given element. And for such applications, actually, binary search is such a powerful tool, and as well as binary search trees. So today, we are going to be looking into what binary search is and how we can apply it on arrays. So, like in binary search, basically there is one precondition, which is the elements that we are dealing with, they have to be in a sorted order. Like, if there is no order, then we don't make any use of whether the values on the right are greater or whether the values on the left are smaller or something like that. So that's why, in order to be able to apply binary search on a given array, that array has to be sorted. So, let's start with an example. Let's say our elements are 1, 5, 11, 15, 28, 47, 99. Let's add one more, 101. Okay. So, if we are searching an element, or like, let's say we are searching an, let's say our query is a number x, and we are looking to find the number that is closest to x. So what we are doing is, we start from the middle. And here, there is no element in the middle, right? So that's why by your implementation, you're going to either choose this guy or this guy. Let's say this is our middle guy. And then we check the value that we have in hand in the array versus the value that we are looking for. Let's say we are looking for 95. Is 95 greater than 50? Yes. In that case, is there a point for looking elements that are on the left side of this point? We know that they are all smaller than the value that we are dealing with. So there is no chance that they are going to be closer to 95 than 50, right? So that's why at this point we check our distance. Like let's say we are going to keep track of the best value. And the distance right now between 15 and 95 is 80, right? So since we didn't have any best value before, 15 is going to be our best value, the closest value that we found to our queried element x so far. And now that we know all these elements cannot be closer to the number we are looking for, which is 95, than 50, there is no point looking on this side of the array anymore. So, moving forward, what we do is, we are focusing on the right half. And then we actually apply the same algorithm, the exact logic again. So, now what is my array size? 5. This time, my middle number is 47. So, I do the same comparison. Is 47 smaller than the value that we are looking for? Yes. Therefore, we are focusing to the right side of the array. So there is no point the elements on the left, which are 15 and 28, can be closer to our requested value, which is 95. And the second check that we are doing is 47 closer to 95 than 50. The answer is yes. So we update our best value to 47. And now we are focusing our effort to the right side. So now that we have two elements, but we have to be consistent with our behavior. In the case of having even number of elements, we define the middle as the one on the left of the middle. So, which is 99. So what I do is, I check whether 99 is greater than our requested value or not. It is greater. So at this point, is there a point to going to the right of 99? No. And I check whether 99 is closer to the requested element from the best value that I found so far. And 99 is actually closer than 47. That's why I update my best value as 99. And finally, what is my subarray size right now? It is 1. So is there a left side of 99? No. That's why at this point, I can confidently return the result that I have in the best value field. This is going to be the closest element in our array to the requested value. So, is everyone clear with the logic? And as you see, actually there is an application where the method can be useful over hash sets. Because if we are not looking for exact match, in that case, hash set is not going to be useful for us. And binary search can actually do way better job. So, now let's look at our time and space complexity. How much of an additional extra space we used here? O1, right? Constant time. We didn't get any arrays with size or n or anything. So, how much of initialization cost do we have to apply binary search? What's that? If it's sorted, nothing. But if it's not sorted, first we have to sort, right? And depending on which sorting algorithm we use, the complexity can change. But like what I'm underlying is, if the given array is not sorted, then we have to sort it to be able to apply binary search over it, okay? So it's something to keep in mind. And when we are looking for the element, what is the time complexity that we get for each query?
O1.
O1?
Yeah.
Why?
For each query being each time we loop, or for each
For each
number?
query meaning each x value.
Oh, in that case, log n.
Log n, right? Because every time we are making a comparison between one element in our array with the requested value, we basically get rid of half of the array from the lookup, right? Because if the value we are looking for is greater than what we are checking right now, then we are going to focus on only the right side of the array. We know that all the elements on the left side are further than the requested value, and vice versa. So that's why every time basically we are dividing our solution space by half. As a result, we can go as much up to log n depth to find the nearest element for a given query. So any questions up to this point so far? No questions? Cool. Now we are going to check out two different implementations of of binary search, but like I made a mistake on the order of slides, so I was going to give the search problem at the beginning and then move to binary search, but since we already covered the good version, let's just think of the search problem. Like there is a naive solution for the search problem, right? Like if we are looking for an element, or even let's say we are looking for an element that is close, that is closest to the given query, like another alternative algorithm that we can use is we can start from the start, right? And check whether that element is closest to what we are looking for or not. And for this naive linear search algorithm to work, we don't also have a prerequisite of sorting the elements, right? We can just compare all the elements against our query and find the closest one is. Okay, so in order to make it very clear, let's also take a look at this example. Like as we said, to be able to run binary search, our array must be sorted. And here we are looking for value 23. And we start from the middle, it is 16, therefore we go to the right. We know that 23 is greater, so it has to be in the second half. And the remaining elements are from 23 to 91. And since we have 5 elements, the middle is 56. And since it is greater than 23, this time we are focusing to the left half. And now we have 2 elements, and in case of having even numbers, it was checking the one that is left to the middle. So we are basically checking whether 23 is equal to 23, and which is true, that's why we are returning the result. So that's just another example of binary search. Now let's take a look at the code. So, like we get the numbers, we get left, right, and the x value that we are looking for. So for this one, instead of looking for the closest one, it is just checking the exact check. But obviously you know how you can modify the method. So the first thing that we should be careful with is the definition of the middle. Like you can either represent it like this, basically in order to get the middle of a given subarray that starts at L and that ends at R, you can just sum them and then divide it by 2. Right? Like you have 2 numbers, how would you get the average? This is how you get the average, right? An average gives you the middle. So that's why this formula works. And after that, obviously, we are just going into our sub-problems. Like if the element is equal, then we just return it. And if it's not equal, and if it's greater, we are looking to the right side. One thing that we should be careful with here is, like the element we are checking is greater than the query, right? So is there a point to check our element again? Is there a point to include the element that we are on again in our search in the next step? No, because it's not equal, right? So that's why we have mid -1 here. So basically it's not just half of the array, but as well as the middle element that we are checking. If there is no equality, we can also get rid of that. When we are going into the left side, we are literally going to the left side, like we do not include the middle element, okay? So likewise, if that's not the case, if we have to go to the right side, again, there is no point in including middle, because it's not equal. So, like that's one thing that you can be careful with. And in the end, if we couldn't get any results up to this point, it means we couldn't find our element. Like if R is not greater or equal to L, our pointers, they actually passed and we don't have any other elements to look for. At this point, we are returning -1 to indicate that we couldn't find the element. Okay? So, any questions about the recursive implementation? Alright. Now let's take a look at the iterative implementation. Like they are not much different than each other. So again, like we start with the same input values and we find the middle likewise. And if we find the element, we just directly return our index. So completely the same up to this point. So the only difference is, instead of making the recursive calls, we just update our current left and right value, and then we keep iterating with the help of the while loop. So, like in terms of performance, I don't think there is going to be a very big difference, because even if we are using the call stack in the recursive version, since our complexity is log n, we are not going to introduce too many elements into the call stack. So this implementation is going to work faster. The iterative implementation is going to work faster than the recursive one, but it's not going to affect your runtime that much, because we are not putting too many elements to our call stack. Like in the case of, for example, Fibonacci, maybe it might make sense to implement it iteratively, because like basically we are making 3 calls for each, so at least it's going to be ON, right? Let's say we were making only 1 call for each subproblem. It was going to be ON, like we were going to be adding n elements to our call stack. But here we are adding log n elements. That's why the difference is going to be less. Okay. And I already add these questions to the sheet as well, so you can start working on them through the progress sheet. And there are actually too many different applications of binary search. Like we can actually add more problems after you guys are done with this. Like it's a concept that can make your job easier in many different problems. And sometimes like one problem can actually have multiple steps, and one of the steps can be applying binary search. So like if you are dealing with sorted numbers, or if you are making some queries to find an element that is close to what you have in hand or something, it is always good to think about binary search. It can be handy. And the second topic that we are going to cover today is heaps. And we will start with binary heaps. Actually, we are going to end there. We are not going to go to more complicated heaps. And heaps are also very useful data structures, and it is very probable to get some questions in the programming interviews about heaps. Like it's not a super advanced topic that is not excluded. So there are a lot of questions which can be solved by heaps and which are frequently asked in software engineering interviews. So let's look at the properties of a binary min heap. Like it's a complete tree. Do you guys remember the definition of the complete tree? So in the complete tree, we didn't skip any of the nodes up until to the last layer. Meaning, like this is a binary tree, right? Everybody has left and right. So this is a full binary tree. Like in the full binary tree, like we have all the nodes, right? And in the complete binary tree, imagine you can only delete nodes in the last level, starting from right to the left. This would be a complete tree. This would be a complete tree. But this wouldn't be a complete tree. Okay? So, the first property is it's a complete tree, like this. And the second property is each node is smaller than or equal to its children. So, if we put together these two information, actually we don't even have to consider the first information. If each node is smaller than or equal to its children, where do you expect to have the minimum value in this tree? At the top, right? The minimum value is going to be at the root. Because if that wasn't the case, then let's say it was inside, it was here, actually this guy was going to be greater than its child, right? So that wouldn't work. Meaning the minimum element cannot have parents under given circumstances. So that's why in a min heap we have the minimum value at the top. So I guess like it might be very trivial to convert the min heap into max heap, right? So if we say instead of each node is smaller than or equal to its children, each node is going to be greater or equal to its children, then we will have a max heap. So depending on your application, depending on the problem that you are dealing with, you can either use min heap or max heap. Depends which value you are looking for. So, now let's take a look on this example. 1 is smaller than 3 and 6. 3 is smaller than 5 and 9, and 6 is smaller than 8. So, also, it is a complete tree. Is this a valid binary heap? And we can also say it's not just binary heap, but it's a binary min heap, right? So the beauty of completeness is that since no nodes inside are skipped, actually we can keep that structure in an array. Like we don't have to build nodes and then left, right, deal with pointers. No need for that. We can completely represent everything in an array. So let's do an exercise about it. Like we had already covered in binary search tree class, right? Because it wasn't about binary search, but it was about binary trees. And then we were dealing with complete trees. We were saying you can easily represent them in an array. But let's just remember how it was working. So basically you can think of, we are starting from the root and then placing every element in the next available slot in the array. So root is going to be here. And the value in root is 1. And the children of the root are, so the first one is its left children and the second one is the right children. So 3 is going to be here and 6 is going to be here. And the same logic applies to this guy as well. So the first children is the first unoccupied cell, this one. And the second children is the second unoccupied cell, this one. And the values inside are 5 and 9. And finally, this one has only one child, the left child. So we have 8 here. And let's put the left and right indicators to make it clear. So this is left, this is right, and this is left. And also if you remember from our last lecture, the formula that we need to reach from a given element to its children is very simple. So, if we are at the ith node, what is the formula for our left child?
Two I plus 1?
Yes. 2i plus 1 is 1, 2i plus 1 is 3. And let's say we had one more child here, it was going to be 7. This is 6 and this was going to be 7. 2i plus 1 is our left child. And how about our right child? 2i plus 2 is our right child, right? Assuming we start our numbering from 0. You can start from 0, you can start from 1, but you got to keep track of which one you start from. And you should be consistent in your implementation. Doesn't matter, no preference over 0 to 1. You can choose whichever you want, but then update your formulas accordingly. So here in the example we started from 0, that's why we are covering the values from 0. And how about, so we covered the formula for the left child and right child. How about the formula for the parent? Because like we might want to go to our children, but at the same time we might want to go up to our parent as well. Basically if we are traversing these 3, we are going to need both, right? So what's the formula for our parent?
I minus 1 divided by 2.
I minus 1 divided by 2. Let's see. It's going to work for this, it's going to work for this. It's going to work for this, it's going to work for this. Yeah, looks like it's working. Cool. And like you don't have to memorize these formulas. You can exactly do what we are doing here. You can just number them and then see whether the formula you come up with works or not. Okay? So, right now we also see that how we can navigate on the binary heap. Does anyone have idea how we can actually build it? Start thinking about it, we are going to get there in a minute. Before heap operations, we are going to talk about different applications of heap. So, let's say we have this structure. Heap is implemented, all the elements of an array are inserted to the heap. How we can sort these elements with the help of heap? Does anyone have any idea? Yes.
we can continuously remove the roots and store them in an array.
Right? Because root will always have the minimum element, right? So if we get the root from this tree, we are going to get 1. And assuming we will implement the methods to keep this in the shape of heap, what is going to happen after we remove 1? The second smallest element is going to go to the root, right? Because if we can call the remaining part the remaining part heap, then it should still satisfy the same conditions. So it is going to be a complete tree, and it is going to have each node is smaller than or equal to its children. So to be able to do that, what we are actually doing is like, if it is going to be complete tree, which node we can get rid of? Like, let's say we are removing root, right? So we get 1 out of here. Which node we can delete to keep it complete tree? Which one? The one, can you please tell me which number is inside? 2? Fifth. So this guy, right? Because if we delete any other nodes, then it's not going to be complete anymore. So this actually gives us a clue about how the operation is going to work. We get 1 out of our tree. Like we say, okay, so we are going to return 1. And in order not to lose our complete tree property, we delete our last element. So deleting a last element in an array means getting your end counter from here to 1 position before. And actually it doesn't finish there, because if I get rid of 8, I am actually losing a value, right? This is not something I want. So what I do is there an empty slot right now? So I'm about to delete 8, but I am also removing 1 from the tree, right? Is there an empty slot right now for 8? Yes. I can basically take this 8 from here, get rid of this edge, and then put 8 here, right? And when I put 8 there, is it going to be still heap? No, because now I don't satisfy the second condition. Okay, so I know that 8 is breaking this rule, right? So in that case, if I'm going to fix this, then I should actually fix this starting from 8. And what can I do? Right now, let's say we are at the root and there is 8 here. How can I fix it? Swapping it with which one? With node 1. And the reason is not because it's node 1. The reason is the value here is smaller than this one. Like, let's imagine we have 8 here. If we replace 8 with 6, is it going to be enough? Because 6 is still greater than 3, right? I need to make more swaps. So we are not going to feel comfortable. It's not going to be a good min here. So that's why I choose the smaller element in my children and then swap myself with that. So what is going to happen is we are going to have 3 up here and we are going to have 8 here. And are we done at this point? No, because 8 is still breaking our second rule. 8 is not smaller or equal to 5. Actually, we are going to apply the same technique here. We are going to look 2 of our children. We have 2 children. And we are going to pick the minimum one. And if that one is smaller than us, we swap with that. Until when we are going to keep doing this?
Larger than the value which
Yes, I actually can have 2 conditions for stopping. The first one is I might reach to the leaf, right? Like once 8 is here, I don't have any children anymore, so there is no concept of whether 8 is smaller than its child or not, because no children. And the second case is it can reach to point where it is greater than both of children. So in that case, it means the heap property is satisfied again. Any questions? We are going to look into these operations in more detail, but I want to have the brain exercise with you before we go look at these operations in detail. So, if we continue working like that, what is going to be our time complexity? So how much time did we spend to keep our heap property after removing an element from root?
Log n.
Log n, right? Because every time, like, we are basically checking two of our children, and then we, like, in the worst case, we swap ourselves with one of them, and we increase our depth in the tree. And every time, like, basically, if we continue making operations, we are going to increase our depth. And it will continue, in the worst case, until we hit to the leaf nodes. So that's why the operation is log n. And how many times do I have to do this to sort all the elements? N times, right? So what is the complexity of heap sort time? N log n. Yes. Now let's take a look at another application. So far we had seen queues before, right? What were queues? Like, queues were basically some sort of like lining concept, but in the previous versions of queues that we have seen, there was one thing. All the elements that were coming into queue, they were equal. So they had the same priority. Therefore, whoever comes the first got the service first, right? We were saying first in, first out. But in real world problems, this is not always the case. Like, imagine we are working at emergency room. Like, there are some patients which are super critical, which are under super critical conditions, and they have to be treated immediately. Let's say somebody is coming after having a car accident, you know? So we have to treat them faster than people whose situation is not as urgent, right? So that's why in emergency rooms they usually use color codes to decide on the priority of the patient. So let's say they have 3 color codes. And in order to simulate what is going to happen in the emergency room, would it be enough to have only one queue? That wouldn't be enough, right? So the first solution before looking into heaps that can come to mind, how we can solve this problem? Let's say we have 3 different priorities. We can have 3 different queues, right? So one queue for each color, and when we are gonna assign a doctor to a patient, first we are gonna check if the highest priority queue has any elements waiting. And if not, then we are gonna go to the previous one, and if that's not the case, then we are gonna go to the least important one, these prior ones. So that would be a working solution, yes. If we know how many different priority levels we are gonna have, then it could work. But imagine a scenario where, like, you are, instead of simulating an emergency room, you are simulating tasks that are going to be run on the cloud, and each task has different priority. And their priority levels can be between 1 and 1 million. Are we going to have 1 million queue? It's not going to be the best solution, right? But what can we do in that case? What kind of solution we can use? Like, we can actually use heaps for that purpose. Like, if we insert things with their priority to heap, then heap can actually help us to find who is the earliest and who has the highest priority. Or we can actually define the priority concept in a way that it will also include the earliness. So therefore, just by looking at priority, we can find which is the next task that has to be handled, or which is the next patient that has to be cured. So heaps, they can directly work as priority queues. Because in the normal queues, whenever an element comes in, there is no way it can pass the ones that are above, right? That are before. It has to wait for all of them. But in priority queue, in heap, that doesn't have to be the case. Like, if we insert an element from the bottom with very high priority, then just by comparing whether this guy has higher priority than his parent, we can take him up. And then if that is still the case, we can take him up. And this way we can keep going up to the root if it's gonna have the highest priority. Okay? So now, like, are you guys clear with how we can use heaps as priority queues? Cool. And once we cover all the heap operations, it's gonna be more clear. And some other applications of heap are like shortest path. Like that's one of the advanced graph algorithms we are gonna see. I mean, it's not that of an advanced algorithm, but we are not gonna cover in the first part of graph traversal algorithms. In the second part, we will cover shortest path. Likewise, minimum spanning tree. So for solving these two problems, using heaps, they can be very handy. I'm not going to go into details yet. We are going to cover them in the course in the future. But if you are curious, if you want to get a feel of how these problems are and how heaps can be used for solving them, feel free to take a look. I'm pretty sure you can find a lot of stuff online. So, now let's focus on how we can run some important operations on heap. So let's have an example here. Let's say we have a mini heap and it would be have 1 and then its children are 3 and 6 and then 3 has 5 and 9 and 6 has 8 as children. Okay. So let's say the first operation we are going to consider is inserting an element. In order to keep our complete tree property, where should we insert the new element?
Last.
Like basically the first available slot here, which is here, right? So this is going to be the place where my new element is coming in. And imagine our implementation in the array. So the end was here. The last element in my heap was here. So when I'm inserting a new element, basically what I do is I consider end plus 1. And place my new element to end plus 1 and update that. Okay? So, now after inserting, let's say 2, what is going to happen? So, before this, do we know that the rest is a heap? Yes. Like that's the assumption that we are working under. We are going to come to point where how we can make a given array heap. But right now we are working with the assumption that the rest is a heap. And when I insert a new element, who can be breaking the rule right now?
New element.
These guys, right? The new element and its parent. And if that is the case, which is the case here, because 6 is not smaller than 2, what I'm going to do is I'm just going to swap them. So 6 is going to come down to here, and 2 is going to go up here. So at this point, who can be breaking the rule? Again, if there is an element that is breaking the rule, it can be this one. It may or may not break the rule, but we don't have any other usual suspects. We're just going to take a look at this guy and its parent, and if they are in the right order, then it means we are heap again. If not, we need to apply the swap operation until we get to the point where the new element is greater than its parent. So, then what is going to be my time complexity for the insert operation? It's going to be log n, right? We start from the last level, and in the worst case, we are going one level up at each step. And this can happen until we hit to the root. And we have log n levels in our tree. That's why the time complexity of insertion into heap is log n. And the second operation that we are going to consider is removing an element. And actually the removal does not have to happen from the root. Like we already considered the case where we are removing things from the root, right? So now to make it more clear, let's do it again. Let's say we are removing root. So we are going to output 1. And in order to keep our heap property, obviously we have to get rid of this node. And what we are doing is we are getting the value here. And then we put it into root, and then we delete our last node. So deleting the last node in replaced. Okay. So let's also apply the operation here. So it was 1 and the right child is 2. And 6 was here. So this was before we start deleting, basically. So now my new end is here. Let's also show that. And at this point, when I want to remove one, like I output it, and then I get the last element, and then I place it into the root. So here this 6 is taken into here. And then I get rid of this node. And getting rid of this node in array implementation is as easy as saying and minus minus. And it's going to start showing here. So am I done right now? No. After taking this element from bottom and making it the king, we don't know whether this guy deserves this position or not. So what we are going to do is we are going to check him against its children. And we are going to find the smallest children, which is the one on the right. And then we are going to swap them. 2 is going to come up here and 6 is going to come here. So again, we are not sure whether we are heap right now or not. So we have to check this guy against its smaller children. And since this is smaller, there is no swap operations needed, and we are done. So right now we see removal from root. What if we remove an element from a random position in the heap? Let's say we are going to remove this guy, 3. How can it work? Actually, the logic is going to be completely the same. We are going to get the latest element, like we are outputting this guy. Let's say we output 3. And then we get the latest element, we remove that node. And then we place the latest value into the node that we want to remove the element of. And after that, obviously, we have to apply again our check. Because now this guy might be greater than one of its children, or maybe both of its children. That's why we compare it against the smaller of its children, and since it is greater than the smaller of its children, we apply the swap operation, and 5 comes here, 8 comes here. So is everyone clear with removal of the root as well as removal from a random position in the heap? And our time complexity is going to be, again, O log n, right? Because what we do is we remove the last node, it is O1, and then we copy it to either root, like in the worst case it's going to go to the root, if we are deleting root. And then we keep checking whether we are heap or not by looking the value of the element that we are dealing with versus its children. And if it is greater than the smaller children, then we apply the swap operation, we have to do the check again. And in the worst case, the node is going to go to the top and then it's going to go back to the latest level again. So the operation is going to take log n time. Okay? So now we are also done with remove. The next operation is modify, and actually modify is not much different than removal. Like once we are removing, we are getting rid of the last guy. And if we are just modifying, then actually we need to make the check 2 ways. That's something that we should be careful with. Let's say we replace 5 with 1. In that case, now this guy can be greater than the smaller kid. That's not the case here. Or it can be smaller than the parent. So that's why we have to do the check both ways. And if it has to move in one direction, then we are going to make it move in that direction. So in this example, it's going to be like this. And again, like at each step, we can either go up once or we can either go down once. And if we are going up, we will always be going up. If we are going down, we will always be going down. And in the worst case, we can do this operation log n time. Because if we hit to the root or if we hit to the leaves, that's going to be our worst case. And it's going to take log n time to get there. And get min, since we have the min heap. How much time is it going to get? Oh, one, right? It's just waiting in the root. It's very easy. What if we have max heap and we want to implement get min? How much time would it take? Oh? Oh, log n. Why? Like basically n over 2, right? I mean, it's going to be O(n). But we don't have to look for the nodes that are inside. Because the nodes that are inside in max heap are greater than their children, right? So by definition, the minimum element has to appear in the leaf nodes. You wouldn't have to do like deal with such scenario, but you can think of this as a brain teaser. Okay, and finally, Heapify. Heapify means we are given an array, it's not a heap, and we are going to convert it to a heap. How can we do that? Let's say the elements we are given are these guys. 1, 5, 11, 15, 28, 47, 99, 101. And let's put them in the random order into this array. Let's see, 28 is here, 5 is here, 15 is here, 99 is here, 1 is here, 11 is here, 47 is here, 101 is here. And I want to make this a max heap. Did I forget any elements? No, we had 8 and we have 8 elements here. Okay. So, let's say I want to make this max heap. In that case, which nodes should I check whether they are breaking heap property or not? Like basically our definition, let's go back to our definition. Our definition says for min heap each node is smaller than or equal to its children. And for the max heap it's going to be each node is greater than or equal to its children. It actually means I can only focus on the inner nodes of the heap, right? Because my definition is like that. If I can make them all satisfy this property, then I'm going to have a heap, right? So I start from the last one, which is 99, like basically the last node with a kid. And then what I'm asking is whether this guy is greater than its children or not. Is this the case? It's not greater than its children. Therefore, we apply the swap operation. So 101 comes here, and then 99 comes here. So, the second inner node is here, right? 15. Like I'm going back. I started from the latest node, which has children. Like imagine this was stored in an array. We have 28, 5, 15, 10, like it was 99, 1, 11, 47, and 101. Initially it was like this, right? Let's go back to the beginning. This was 101, and this was 99. So first off, how am I going to decide like what is the last node that has at least one children?
You can get the size of the array
Uh-huh.
and then minus 1 divided by 2.
Which is actually the parent of the last element, right? If I'm looking the latest parent actually is the parent of the latest leaf, which is the last element. So the parent of this is the formula that you said, which is position minus 1 over 2 is going to give us the parent. And which is here? 0, 1, 2, 3, 4, 5, 6, 7. 7 minus 1 over 2 is 3. So it actually points us here. So this is our last parent. Last parent. And then we start from this guy and we say, hey, am I greater than my children or not? That's not the case. Therefore, we apply the swap operation. So this becomes 99, this becomes 101. Because I'm trying to build a max heap. And let's apply the same operation here. This becomes 99, this becomes 101. So, what I do is, okay, so right now this guy satisfies my condition, right? And if I can make it so that all the inner nodes satisfy the condition, am I going to have a heap? Yes, right? So that's why I keep moving to the left. So this guy now, it satisfies my condition. So now let's take a look at the second one. 15. Is 15 greater than the greatest of its children? No. Therefore, we apply the swap operation between 15 and the greater of its children. 47 and 50. So here, 47 comes here, and 15 goes here. We had the swap between these two. And now, can I tell that 47 also satisfies our condition? Right? Because we checked with the children, and then now it satisfies. So I keep going back in my array. Now I'm dealing with 5. Is 5 greater than or equal to the greatest of its children? No. Therefore, we apply the swap operation. 101 comes here, and then 5 goes here. And the same here. So last parent is back to here now. Last parent. And now that I also make this inner node satisfy my heap condition, finally I am up to the root, right? We will ask the same question for the root. Is root greater than the greatest of its children? No. Therefore, we are going to apply the swap operation. So this guy is going to be 28, and this guy is going to be 101. Wait, what happened here? How?
We need to recheck all the parents.
After the swap, we basically need to heapify the call here as well. So I actually forget one step. Let's revert it back. So 101 was here, and what was our initial version? This was 28 and this was 5. It was like this, right? Yes. Okay. So here, I heapified this one. Okay, when I was heapifying 5, I check whether 5 is greater than or equal to the greatest of its children. And that's not the case, right? I do the swap. And when I do the swap, right now, there is a risk that this is not heapified. Right? So at this point, I also call heapify for this guy. And then, this basically checks its value with its children. And since it is smaller than its children, we do the swap. So 99 goes up here, and then 5 comes down here. So let's do that, and basically this is going to be 5, and this is going to be 99. Like, this is important. When we do the swap, we need to heapify our children again, because we are taking the risk that this guy now can be, may not be satisfying the condition. The previous value was satisfying the condition, that's why we get the tick. But every time we make the swap, the tick is removed, okay? But now that we do the check, we can put the tick again. You can think of this way. So, okay, so now we have the same states. And now that we also heapified this guy, we can go up to our root. And is root greater than the greatest of its children? No, that's not the case. Therefore, we do the swap operation. So 28 comes down here, and then 101 comes up here. And now we don't have this tick anymore because we applied the swap operation, right? So again, we are going to heapify this guy. And what is our heapify operation? It's checking us against our greater of the children. And if the greater of our children is greater than us, then we apply the swap operation. So 99 comes up here, and 28 goes down here. And we remove this tick here. And is 28 greater than the greatest of its children? it is the case. Therefore, we stop swapping. And finally, we took our root as well, and we heapified our array. So is everyone clear with the operation? So this might look like it is actually taking n log n time. Like basically when we are applying the heapify operation for a node, it can go, like in the worst case, it's going to go up to the root, right? So it's going to take log n time. But actually we are not applying this operation for n time. We are applying it for n over 2 time. What was our start position? It was the first parent, right? We didn't start from the leaf nodes. And because of that, it actually decreases the amount of computation that is needed. And like there is a like little bit of complicated proof of this, which actually proves that this operation is done in O n time. If you guys want to take a look, you can search it online and find the proof. But I'm not going to go into the details of that now. Because like practically speaking, we don't need the proof, right? But you should know that the operation is O n time. Okay? All right. So now that we covered all our heap operations, I think it's time to start with, it's time to continue with our programming exercises. And that's it for today's lecture. Thank you very much. But before we close, what do we have at the end of the lecture? The code of the day, right? And today's code is coming from a guy called Albert Hubbard. I don't know who he is, but his code is good. The greatest mistake you can make in life is to be continually fearing you will make one. Because if you are afraid of making mistakes, you're not going to make things. You're not going to try new things. You're not going to get out of your comfort zone. It's okay to make mistakes. As long as they are not super costly, you can revert things back. I mean, obviously you don't want to kill a person, right? You cannot take it back. So it's not about for all the mistakes, but yeah, by fearing from making mistakes, actually we put a lot of boundaries for us. And it's better not to do that. Thank you very much.